Okay guys, now in this part we are moving to the solved examples on the electric potential energy, and the first problem in this part will be the 16th problem in the document. In 16th problem we have a salt crystal which can be assumed to be in the shape of square and whose corners is an arrangement of the sodium and chlorine ions. Here in this crystal, the sodiums are positive ions. It has plus elementary charge, while the chlorines are the negative ions. They have negative elementary charge. And let me just remind you the elementary charge. This is the elementary charge 1.602 times 10 to minus 19 coulomb. And actually this is a standard notation to show the ions. If this is Na plus, sodium plus means it is a positive ion and it has this charge, while the chlorine negative means the negative chlorine ions, it has this charge but the negative, alright? So chlorine charge is negative 1.602 times 10 to minus 19 coulomb, while the sodium ions have 1.6 positive 1.602 times 10 to minus 19 coulomb. Alright, let me read you the problem. A salt crystal can be assumed to be in a shape of square whose corners are an arrangement of the positive sodium and negative chlorine ions like this. Alright, one corner is positive sodium ions, the other corner is negative chlorine ions. And this is negative chlorine ions, and this corner is the positive sodium ions. Now the question, let me just remind you, each ion carries an elementary magnitude of electric charge, and it has two parts. One part is asking to calculate the electric potential energy in a salt crystal. Alright, so we are going to calculate the electric potential energy stored in this arrangement. And second part is asking how much work we need to pay to remove one of the sodium ions. Okay, it doesn't matter which one of them, we are going to pick one of them and then calculate the work or energy we need to give or take to remove one of the sodium ions. Actually, just let's reread this problem. How we can calculate the electric potential energy stored in the system. Actually, electric potential energy, let me make some notes. Electric potential energy is equal to the work against the electric force while we assemble the system of charges. What I mean is the electric potential energy stored in the system is equal to the work we are doing against the electric force while we are constructing this system. What constructing means? Okay, let's start to solve it. I'm going to redraw this figure, but a little bit small. Actually, the side of this square is also given in the problem. You can read it. I'm going to give during the solution. So we have this square, but we don't have any ions yet. All right. Where are the ions? Ions, we assume that are at the infinity. Here are like we have 4 ions in the problem. So these are the ions at the infinity. This is positively sodium ion, and this is negative E and negative E. These two are the chlorine ions, okay, negative ions. So the electric potential energy in the salt crystal is simply the work done against the electric force while we are bringing these charges from infinity to the corners. Okay, so I'm going to take the charges one by one and bring them, and while I'm bringing this to the square, I'm going to work against the electric force. So let's pick up the first one. Okay, what is the electric force acting on the first one? Actually 0, because there is no charge in the system yet, right? So there is no charge generating an electric force. Actually, I can bring it to this corner, like as a sodium, positive sodium ions. But since there was no electric force during the path, actually the work against this electric force, W1, will be equal 0. Now, I'll take the second one. Again, it's a positive sodium ion, to bring it to this charge. But now we have one charge in the system, like sodium ion. It will generate some electric force on the second ion, and we need to work against this electric force. And the work, which will be equal to the electric potential at this point, right? Let's call it like VB. Electric potential at V2, let me call it V2 here. V2 times the Q, the charge of the objects we are bringing, which is simply equal to the elementary electric charge. So the work actually simply be equal to the electric potential here generated by the first ion we brought times the charge of the objects we are bringing. And what is V2 here? Remember, the V for point-like charge is simple K Q over R. K is Coulomb's constant, Q is the charge of the source, and R is the distance to the point we are interested in. So if we write V2 will be equal K, Q is simply equal E over R. R is, let's call it, the A is the side of one side of this square. So I can write R will be equal here, A times square root 2, distance from this point to here, times E is the charge of the objects, the ion we are bringing. So if you plug the numbers, this is the work, W2, the work to bring the second charge to the system. So I can write V2 will be equal K times E, which is 8.99 times 10 to 9th. What was the unit for K? Newton meter squared per coulomb. Times E squared we have here. So 1.602 times 10 to minus 19 coulomb squared over A is given like 0.25 nanometer. Alright, but we need to convert it to the meter, so it's going to be like 0.25 times 10 to minus 9th meter. Alright, here I'm converting nanometer to meter. And if you use your calculator, W2 will be equal 6.5 times 10 to minus 19 joule. Alright, this is W2. Alright, so to bring the first charge to this corner, we don't need to work against electric force because there was no charge in the beginning. Then work 1 will be equal to 0. But for the second charge, while we are bringing it, there is a charge in the system. It is going to generate an electric force. We need to work against that electric force, and that work will simply equal to the electric potential at this point generated by the first charge times the electric charge of the object we are bringing. And when we plug it into the equation, we are going to find W2, the work to bring the second charge, this much, 6.5 times 10 to minus 19 coulomb. Now, we just take two of these charges to the crystal. Now we have two chlorine ions to bring from infinity. Now I'm going to take this one and bring it here, but we already have two charges in the system. I'm going to bring this to this square, and I'm going to call it V3, and W3 is the work we should do to bring this third charge to this corner, and you can write it in terms of V3, the electric potential generated by these two charges now, because they are in the system, times minus E. Minus E is the electric charge of the chlorine ion. Alright, what is V3 by using this one at this point? So these are the distances from two source charges. So V3 will be equal, for this one, K times E over A. A is the distance, plus from the second charge again, K, its charge is E, and the distance is E again. So I can write 2K E over A is the electric potential generated by these two forces. So to bring the third negative charge to this corner, I can write V3 times E, so which is equal to 2K E over A times minus E. So 2K E over A times minus E, which will be equal minus 2K E squared over E. All are given. You just need to plug the values. For K, 8.99 times 10 to 9th. For E, 1.602 times 10 to minus 19 coulomb, but you need to take its square. And A is 0.25 nanometer. We need to convert it to the meter by multiplying it by 10 to minus 9th meter. So if you plug it, you will find W3 will be equal, let me check my calculations, will be equal minus 1.84 times 10 to minus 18 joule. All right, this is the work we need to do to bring the third charge to this corner. Now it is here, chlorine ion. We have only one charge at the infinity to bring to this corner, okay? And I'm going to call the potential here V4, which is generated by these three charges. All right, now I need to make myself some space, so we calculated W1 for the first ion, which is equal to 0, W2 to bring the second sodium ion, which is here, the result. The third charge, which is the first chlorine ion, to bring here. This is the work I need to do against electric force. Now it is turn to bring the fourth chlorine ion to the corner here. Now again, the work we should do against electric force, here it is chlorine. I am going to bring it to this point. We can write V4, the electric potential generated by these three charges, times the charge of the chlorine ion, which is negative E. So V4 will be good. Again, the electric potential generated by those three charges, and since it is a scalar, I can just add the scalar potential at this point. So from here to here, all right, there the distance is A, so I can write K E over A from the first ion. From the second sodium ion, I can write the distance is again A, K E over A from the second sodium ion, but we have also now the chlorine ion here, and the distance is R, which is equal A square root 2, but we need to put negative because it has negative E over R times square root 2. If I just simplify it, I can write it, it's going to be equal K E over A, right, times 2 times square root 2 minus 1. Am I right? Seems, am I right? Okay, again, I suggest you to check my calculations in case if I do some mistakes. And if you check and find my mistakes, actually, it is a good practice for you to review the solutions. Okay, so I'm going to use this to calculate the work we need to do to bring the fourth ion into this corner. And it is going to be here again, like K E over A for V4, 2 square root 2 minus 1 times minus E, which is the electric charge of the chlorine ion we are bringing from infinity. So I can write it again, minus K E squared over A, 2 square root 2 minus 1. And if you plug the numbers again, K is given, E is the elementary charge, A is the side of this square, which is 0.25 nanometer. And this is just the factor coming from the simplification. Now, if you plug the numbers, use your calculator, you will find the work to bring this fourth charge minus 2.38 times 10 to minus 19, or 18, sorry, 18 joule. All right, so we brought all charges from infinity and assemble a salt crystal. Now, the electric potential energy is again nothing but the total electric work, we need to do against the electric force. So what does it mean? The electric potential delta U in the system is total work, which is what we calculated as W1 plus W2 plus W3 plus W4. Alright, so we calculate W1 is 0, W2 is 6.5 times 10 to minus 19 coulomb, and W3 minus 1.84 times 10 to minus 18, and for W4 we calculated what? Let me just write it here, minus 2.38 times 10 to minus 18 coulomb. If you add all of them, you will find, actually, let me check my result. You will find, okay. All right, you just need to add them. I forgot to write the result here. Oh, no, it is not 2.8. I calculated it wrong, so you can just, you can correct it in the previous calculations, which is equal minus 1.19 times 10 to minus 18 coulomb, and if you add all of them together, you will find minus 2 times 38 joule times 10 to minus 18 joule, which is the total work you should do against the electric force to construct this salt crystal, which is going to be equal to the electric potential energy included, stored in the system. But it has a negative electric potential energy, so think about its negativity. All right, think about this negative electric potential energy. Try to understand or try to read what it means. We are going to discuss maybe later, but for now I'll just leave it to you to think about this negativity in the electric potential energy. All right, the second part is asking how much energy do we need to remove one of the sodium ions. All right, so let me just draw the figure again. We have this shape like sodium ion, another sodium ion here, a chlorine ion negative, and another chlorine ion negative here. So let's assume that I want to remove this sodium ion. Okay, what is the energy of this sodium ion here? The energy of sodium, the electric potential energy of the sodium ion. Here. Let's say delta U and A plus, which is simply equal, let's call the V, the electric potential here. Potential here. So V times the charge of the sodium ion, which is simply V times E. The elementary charge is the charge of the sodium ion. So we just find what is electric potential at this point. The electric potential at this point is simply generated by this ion, and this ion. So let's just write it. From this ion, the distance is A square root 2. We already discussed this. So K E over A times square root 2 is the electric potential generated by this. And now from this, see, this is the distance. K E over A is the electric potential generated by here, but it has a negative charge E, so we need to put a negative sign here. And we have another chlorine here, also it is generating an electric potential here. So K E over A is the distance, but again it has a negative charge. We need to put another negativity here. So if I simplify this this equation, I will find Ke over A minus here times, let me see, 2 square root 2 minus 1 over square root 2 is the electric potential. If I plug the numbers, Ke, the distance, the side of this crystal, and the number factor here, we will find it is actually negative 7.45 volt. Right? All right, I'm forgetting the factor here. Okay. Ke. No, it should be okay. All right, negative 7.45 volt. So if I plug this number here in the equation of the electric potential of this sodium ion, Na plus, by multiplying with its charge, we will find minus 1.19 times 10 to minus 18 joule. All right, now again we have a negative energy, electric potential energy for an ion. Let me just give you the hint what the negativity in the electric potential means. This is a system in which the charges are bound each other, right? This is a bound state. And this bound state is creating a salt crystal, and if the charges are bound each other, their electric potential energy will be negative. So how much when they can move away from this system? Actually, when their electric potential energy is at least 0, then they can move with each other. So to move one of the sodium ion, we need to make its energy at least 0, right? How we can make the 0? If we give this much this much energy to the sodium ion, its total energy will be equal 0. And once it is equal 0, it can be removed from the salt. So let me just make some notes. To remove one ion from the system, we need to make its total electric potential energy at least 0. All right, it could be greater than 0, but it couldn't be less than 0, at least 0. So to make this much energy 0, we need to give, hence, or thus, we need to use the following energy to remove one sodium ion. So that is the energy we should give to the system, which is the same amount but positive, times 10 to minus 18 joule. If we give this much energy to the sodium ion, its total energy will be 0, and then we can remove it. All right, so we need to give at least this much energy to remove one ion. All right, hope it is clear. Now let's move to the next problem. In this problem, actually, we calculate the electric potential energy stored in a salt crystal by bringing the point-like charges one by one. But what if we have total charge Q? All right, this is total charge Q, but we distribute it, and what we bring it to this sphere and charge it such that its volume charge density will be rho. All right. Actually, it takes us to the next problem, problem 17. Let me first write it. Problem 17 asks us to calculate electric potential energy stored in a charged sphere. Now in this problem, actually quite similar, but in this problem we have a charge distribution rather than point-like charges, and that the total charge Q will be distributed within a volume of a sphere here. Okay, let's say its radius is r, and through the volume such that rho, the volume charge density, will be uniform or constant. So how we can calculate the electric potential energy when we charge this sphere with the total charge Q? Actually, it is again the electric potential energy is simply equal to the work done against the electric force while we are assembling this spherical charge density. So first let's assume that the Q total charge is distributed at the infinity. Alright? This is the infinity, and we are going to bring the charge, but not at once. Actually, we are going to take small charges dq, bring it here and distribute it here. Alright? From 0 to some spheres. And we are going to cover all these spheres such that the rho will be always constant. So once I bring the dq and distribute it here, let me just draw it again. This is the center and r. So I bring dq and distribute it here. So rho is the charge density of this, but all these parts are still neutral. So I'll bring another dq here and distribute it here, here, and keep bringing dq to cover all the sphere. And at some point, for instance, if we already bring some charge q, that dq feels some electric force, we need to work against this electric force. So what is the electric force? F will be equal k, q, the charge over here, out of the r, let's say its radius is r, out of the r is just point-like charge, q dq over r squared, right? We are going to bring up to here. Alright, so it's going to feel this much force, and once again the work to bring this dq charge here, it's going to be like F times dr, but we need to integrate it because that F is a function of the distance. Alright, to bring the Q here, but again we keep rho, the charge density, constant, so rho will be equal constant, and it's like Q over the total charge we bring, volume of this sphere. Alright, what is the volume of the sphere? It's simply 4/3 pi r cubed, the volume of this sphere, and if we use it, actually rho will be equal Q over 4/3 pi r cubed, or I can write Q in terms of the charge density and the radius of the sphere we already assembled. We can write Q is equal rho times 4/3 pi r cubed. Alright, so see, Q will also depend on the distance, on the radius of the sphere, and by using this I can write dq will be equal rho times 4 pi r squared dr. I just take the derivative of this side with respect to the r and we find this one. So we are going to use here, actually from to here, what r is changing. Actually we start from the 0 point and at the end we are going to cover all the spheres, so r will be changed from 0 to r, the radius of the sphere, and just we need to integrate this work to calculate the total work we need to do against the electric force to assemble this sphere. So let's start first solving. Alright, so work, let me just write again. Force will be equal k q dq over r squared, and then the work will be equal F times dr, because the scalar multiplication, and we need to calculate the, let me just plug this here, Let me just remind here, we already had Q and dQ. So Q is equal rho times 4/3 pi r cube, and dQ is rho times 4 pi r squared dr. I need to put them here, plug it into the equation. So dW, the work to bring this dQ into the sphere, we can write K. For Q, we have rho times 4/3 pi r cube. And for dQ, we have again rho. Let me put some in the parentheses. Rho times 4 pi r squared dr over r squared. And that's it. Yeah, I think that's it. F here. All right. Okay, let me also check my all right. Okay. QR cube dq. There is no dr. All right. Okay, this is force, this is dr, but actually I need to write the potential. Okay, the potential R will be equal R, right? The potential. Because for work, we are using V times dq, the potential. All right, so we need to integrate it to get the total work. We need to integrate it from 0 to R, the radius R changing from 0 to R, the whole radius of the sphere, K. If we simplify it, let me just check my notes. If we simplify it, we will find K from here, rho squared, 4.3 and 4 pi, so it's going to be like 16 pi squared over 3 r5, but we have another r, so we have r4 and dr. For k, to simplify it, I can just write 4 pi epsilon 0. If I plug it here, the work will be the integration from 0 to r, and 4 pi over 3 epsilon 0. You just plug it in here and simplify the equation, rho squared r4 dr. So we need to integrate, take this integration to calculate the total work against the electric force to assemble a charge distribution, spherical charge distribution. Okay, let me make myself some spaces. All right. Okay, work will be equal. Let me put some constants out of the integral. 4 pi, 3 epsilon 0, rho, we assume it is constant. It's going to be from 0 to r, r4 dr. So this is a simple integration. We can find 4 pi, 3 epsilon 0, rho squared, r5 over 5 will be the result of the work should be done against the electric force, and actually it's going to be equal to delta U equal work. This is the electric potential energy stored in a charged sphere. All right. Actually, we can keep simplifying this system again. How? We have the charge density here, so we can write the total charge. The total charge of this sphere is Q, and it will be like rho, the charge density times its volume, and we know this volume is nothing but the volume of the sphere, pi r cube. From here, rho will be equal 3 over 4 pi, right? R cube times Q. If I plug it into here, I will find the total work will be equal 3/5, 1 over 4 pi epsilon 0, Q squared over R. And what is this again? You can also write K. So it is like 3/5 K Q squared over R will be the total electric potential energy. Let me just write, stored in a charged sphere. Alright, so it is the total electric potential energy stored in the charged sphere. But before moving a second problem, let's do the same calculations, but now we are going to charge only surface of the sphere. Alright, actually I'm going to write the same problem, but not for the volume charge density. Now we are going to have a surface charge density. So we have a sphere here, forget about the volume, and the question is calculate the electric potential energy of a sphere if it has a surface charge Q uniformly distributed. Alright, now we have Q, but we distributed is over the surface, so sigma is the surface charge density. Alright, charge density, and actually this is again the same surface R. Now the electric potential energy of such a charged surface will be again equal to the bring all the charges from infinity and distribute it over the surface. So the electric potential at this point will be simply equal like K Q over Q. Let me just draw again. Okay, this is the problem. And we are going to, first I'm going to put this sphere, and all Q is at the infinity. This is neutral in the beginning. So I'm going to bring some dq and put it here. Another dq, put it again the surface, and keep bringing dq's here. Assume that at some point we already bring some charge q. So this dq, when I bring this dq to the surface, I need to work against the electric force generated by this q. So what is the, I can write this work, dV, like V, the electric potential at this point generated by this q times dq, the charge that we are bringing from the infinity. And V, we actually calculated the electric potential of such charge distributions, and at this point, let's say it is r, the radius, it's nothing but kq over r. So the work I need to do against the electric force is simply dW will be equal kq over r times dq. Alright, and actually I can use q, but r will be constant now. R is not changing because we are on the surface, and the distance of the surface from the center is always the same. So I just need to integrate it. The V should be dW, and it should be integration of k q over r dq, and q will change from 0 to its total charge q. And this is an easy integration. I can write k over r q squared over 2 from 0 to q, and if I put it, it's going to be like 1/2 k q squared over r. Alright, let's now, actually we calculate the total electric potential energy because it's going to be equal to this W, right? The work we do against the electric force. So this is the total electric potential energy if we distribute charge Q over the surface of this sphere. Alright, let's play with this a little bit more. I'm going to write again. So we have a charged sphere. Q is distributed over the surface with the sigma uniform charge density, and the electric potential energy of such a sphere is 1/2 k q squared over r. What is k? It's 1 over 4 pi epsilon 0, and then if I plug it into this equation, we find delta u will be equal 1/2 q q squared over 4 pi epsilon 0 r. Now, we actually calculate the energy before in a video of our lectures, and we find this can be a capacitance, right? Because we can store this much energy into it, and we can use it later maybe to get the benefit from this energy. And we calculate the energy like in this one, 1/2 q times v, or we can write 1/2 cv squared, or we can also write this 1/2 q squared over c. So let's take this equation and compare it with these two. 1/2 we have q squared, and this is the capacitance. By comparing with this equation, we find 4 pi epsilon 0. Actually, when we calculate the capacitance of a single isolated charged sphere, we found this is the capacitance. So actually, without knowing or discussing the capacitance, just calculating the work against the electric force, we also find this equation, which is simply which can simply be written in terms of the capacitance of this charge sphere. All right, so this is the total energy, electric potential energy stored in the charged spheres. First, we discussed the electric potential energy when we distribute the total charge Q within a volume of a sphere. And the second step, actually, we considered what happens to the electric potential energy if we distribute the total charge over the surface of this sphere. And we find this much energy we can store. And actually, this is consistent because we can write it, the total electric potential energy, in terms of the total charge and the capacitance of the system. And comparing these two equations, we can find the capacitance is 4 pi epsilon 0 times r. Actually, this is what we found when we discussed the capacitance of a single isolated sphere. So the next part, actually, we are going to move to the solved examples about the capacitance. And let's start with the 23rd problem in the document. All right, let me clean this up. All right, it's with a simple capacitance problem, 23rd. So you can read it yourself, but I just read here out loud here also. If a drop of liquid has capacitance of 1 picofarad, what is its radius? So actually, it is asking if a drop can provide a capacitance of 1 picofarad. What is its radius? First of all, we assume this is the drop of a liquid, and we assume it is a shape of a sphere. All right, so it has a radius. So we need to first remember what this is, and now a charged single sphere, right? To calculate this the radius, I can write its capacitance like 4 pi epsilon 0. Let's say its radius is r. This is the capacitance of a single isolated sphere. And this sphere is here in this problem, a drop of a liquid, and this is its capacitance, and it is given like it is already 1 picofarad, which is 1 times 10 to minus 12 farad. We need to use this one. All right, so if I plug this here, 4 pi epsilon 0, actually we know they are varies. So r from here, I can write c over 4 pi epsilon 0, and this is 1 times 10 to minus 12 farad over 4 pi epsilon 0. This epsilon 0, actually its value is known, 8.85 times 10 to minus 12. And by using this equation in your calculator, you can find r is nothing but 0.009 meter, or we can write 9 millimeter. So if the drop of a liquid has this much capacitance, has a capacitance of 1 picofarad, or 1 times 10 to minus 12 farad, if we assume it is a shape of a sphere, its radius should be 9 millimeter. All right, this is just a warming up about the capacitance. Now let's consider the energies of the capacitance we can store, which takes us to the problem, 24th problem. All right, problem 24th. Let me just read it out loud for you. A 12-volt car battery is being used for charging a 100 microfarad capacitor. So we have a capacitor. Let me just draw it. We have a capacitor here, and we just connected to a battery which can provide, let me see, which can provide 12-volt electric potential, and this is C is 100 microfarad, which I can write 100 times 10 to minus 6 farad. And it is, first part, it is asking how much energy will be stored, in this capacitor. So just let me remind you, it's going to be full when, let's say, Vc is the electric potential difference here. The capacitor will be fully charged when Vc is equal to 12 volt, right? When the electric potential difference of the capacitance is equal to the electric potential difference of the power supply, then it's going to be fully charged. So the energy of the capacitance can be written. Actually, we wrote it in the previous problem, the one before the previous one. Energy of the capacitance you can write like delta U, nothing but 1/2 is capacitance times the square of the electric potential difference, which is given like 12 volt. So if I write 1/2 times 100 times 10 to minus 6 farad, we need to use farad even though it is given in microfarad, times 12 volt squared. And if you use your calculator, you will find the electric energy stored in this capacitor is 0.007 joule. So this much energy can be stored in this capacitance. Now in the second part is asking actually us to calculate the electric potential energy in the battery itself and compare with this one. Okay, and we assume that the battery can provide some charge which is given 3.6 times 10 to 5th coulomb. So in part B, actually it is asking us to calculate the energy of the battery. Okay, so part B, electric potential energy stored in the battery. Battery, if its charge, total charge is Q, let me just check my notes, 3.6 times 10 to 5th coulomb. Now, actually we are going to use another equation for the electric potential energy. Remember, I wrote like 3 versions of this electric potential energy, and here now we are going to use 1/2 the total charge times the electric potential version. So the total charge is already given, 1/2, so 3.6 times 10 to 5th coulomb, and the electric potential is 12 volt given in the problem, 12 volt. Just pay attention, we don't have voltage squared, we have voltage itself. So if you use your calculator, you will find the energy in the battery, stored in the battery, is 2.2 times 10 to 2 joule, or you can just write 1200 joule. Am I right? Yep. So this is the energy stored in the battery. And see how much more, I mean, it is great in compared to the energy stored in the capacitance, right? It is like 0.007 joule in the capacitance. Still, it has plenty energy stored in the battery. All right, so this is like calculating the energy of the things. You can follow some other problems. You can find some more problems to calculate the energy inside, energy stored in a capacitance or battery. Now we are going to move the electric circuits and see how we can have the connection, how we can create the connections of the capacitance and resistance as well. So it takes us to the problem 31 in the document. All right. And now problem 31. We have a capacitance in problem 31. Actually, the solution of this problem has already included in the slides I already shared with you. But let's just discuss here together so I can go fast. Now we can have capacitance, let me remind you. And if this is parallel plate capacitance, you can write its capacitor, you can write its capacitance like A over D times epsilon 0. A is the area, and D is the separation, and epsilon 0 is just the dielectric constant. But when we put a dielectric here with the dielectric constant kappa, let's call it C0 capacitance in the air. And when we put a dielectric material inside the capacitor, it's going to modify this capacitance, and now the C, we can write the dielectric constant of the material times C0. C0 is the capacitance in the air. So kappa here is the dielectric constant of the material. We sometimes call it dielectric material. Alright, this is just a reminder. Now in problem 31, we have a capacitance. Let me just draw it here. We have this capacitance. L is the length, so the area is A. L is the length. Alright, and the separation is D here. But we have some dielectric here. For instance, here we have kappa 1, a dielectric. Let me just make this one. We have, let me use another one, two dielectric materials in the other half. Alright, so this is kappa 2 and kappa 3. So this is different, and this is another one. Alright, and let's say the capacitance of this side is C1, this side is C2 and C3. And asking first, in the first part, write C1, C2 and C3 in terms of C0. The C0 is the capacity of the system in the air. In the air means there is no dielectric materials here. C0, A and D. A is the area of the place and D is the separation. So let me give, the length of this side is L over 2, while the length of the other side is also L over 2. Alright, so C0 is, let me just write it here. C0 is its capacitance in the air. It is simply like its area over D times epsilon 0. Okay, but now C1, how we are going to understand this system? Actually, this is a connection of three different capacitors here. Actually, we can make three different capacitors out of one capacitor by using different dielectric materials inside it. But how they are connected? Are they connected serially or parallelly? To understand this, we can send an electron from this side. Let's assume that if we are sending an electron from here, it's going to pass through all the way through C1, right? To come to the other part. So this is one electron. If we send another electron here, actually these two electrons means two different currents, okay? It's going to pass the third capacitance first and then enter the second one and goes it. See, this electron is not passing through on any of this, but only the C1, while the second electron is passing through all these two capacitors. It means these two capacitors are in serial connection. But here, actually C1 is parallel connected to the other half. So actually we can draw a circuit which is equivalent to this one like this. let's say this is point A. Let's just write this is A and this is B. So from point A we have C. Just 1 second. These 2 electrons means like we are splitting the current, okay, here and here. Let's say I1 and I2, and one current is passing through C1, and the other current is passing through C3 first, and then C2, and then they're coming to the point B. All right, this is C3, C2, and C1. So actually this circuit or this connection is equivalent to this structure of the capacitance. Now we need to write first, to answer for part A, we need to write C1, C2, and C3 in terms of C0, area, and the D. So we are going to get back to this circuit. Let me first clean this up, and I'm going to draw it again. Okay. So we have this, let me just make it a little bit smaller. This is C1, all right? And this is C2, C3, we have kappa 2 here, we have kappa 3, and here we have kappa 1, and the length is L over 2. So for C1, what is the, if we just if we get the half of the length of the plate, what is the area here? The area should be A over 2 also, right? So I'm going to write C1 will equal kappa 1, right, times C0, but the first part. And C0 first part, area is not the whole, but A over 2, so it's going to be kappa 1, A over 2, it's area over D. The separation is the same, right? So I can write it like kappa 1 over 2, A over D. I need to write epsilon 0 also, epsilon 0. And this is what? From here, C0. So C1 can be written in terms of like the C0, A and D, actually, or kappa. I can write kappa 1 over 2 times C0. And now C2, the separation is also different, right? Here is D over 2 given in the problem. Also here is D over 2. So I need to write C2 will be equal kappa 2 C0, but the second part, by using this equation again, kappa 2 and C0 is A over 2, the area of the plate, and the separation D over 2, right? So if I can cancel these two, it's kappa 2, there should be epsilon 0 here, A over T epsilon 0, and this is nothing but C0, so I can write C2 equal kappa 2 C0. All right, now finally let's calculate the capacitance of the third part. C3 again, kappa 3 and C0 3 and kappa 3 times. C0 3 is, again, by using this equation, its area is A over 2, its separation is D over 2, and I need to put epsilon 0. I can cancel these twos. Kappa 3, A over D, epsilon 0, and again, this is nothing but Z0, so C3 will be equal K3 times C0. All right, so this is the answer of the first part. Let me just summarize here, and we are going to move to the second part. All right, so let me just summarize here. I have C1 in the figure, like kappa 1 over 2 C0, C2 kappa 2 C0, and C3 kappa 3 C0. Now the second part is asking what is the equivalent capacitance of the whole system. And let me draw you the circuit which is identical, which is equivalent to our structure, like here. All right, this is C1, C3, and C2. And you know how to calculate the equivalent. I mean, we need to calculate first equivalent capacitance of this system, and we can do part by part. First here, C equivalent 2 and 3. These are serially connected, right? So we can write to count 1 over C equivalent 2 and 3 1 over C3 plus 1 over C1. And from here we can write C equivalent to 3 is equal C2 times C3 over C2 plus C3. Okay, but now we move to this circuit. This is C1, this is C equivalent to 3. So the total C equivalent now here, total C equivalent, we can just write simply, it will be equal C1 plus C equivalent to 3, which is from here, the C equivalent of the system, whole system now, C1 plus C2 times C3 over C1 plus C2 plus C3. Alright, so we get the equivalent capacitance of the system, but I need to write it in terms of kappas and C0s. Let me now clean this. Alright, C equivalent of the system. Let me just write the system again. Here we have C1 kappa 1, here C2 kappa 2 and C3 kappa 3. And the C equivalent of this system is C1 plus C2 times C3 over C2 plus C3. Now I'm going to use this equation. C1 is kappa 1 over 2 C0 plus here C2 is kappa 2 times C0 and C3 is kappa 3 times C0 over kappa 2 C0 plus kappa 3 C0. And if, see, we have C0 squared here, but one C0 here, we can cancel. If we simplify this equation, I can write kappa 1 over 2 plus kappa 2 times kappa 3 over kappa 2 plus kappa 3 C0 is the equivalent capacitance of this system. Alright, so actually we answered part A and B. In part C is giving you some values of for K's, kappa 1, kappa 2, kappa 3, the area and the D to calculate the equivalent capacitance. So you can plug those numbers into this equation to answer this. So I skip that part and I'll give it to you. I'll leave the solution to you. Okay, I'll give it to you as a practice. All right, let's move a little bit faster, which is already 1 hour, but I want to finish some problems. Now, next part, actually, you can practice to calculate the equivalent capacitance and equivalent resistors by yourselves by considering some problems. Actually, the document I sent you already have some problems about calculating the equivalent resistance and the capacitance. But these are simple. Actually, you have been practicing since high school, so you can do yourself. In this part, I'm going to move to the Kirchoff laws, but let's take a 5-minute break before doing it. Okay, guys, I'm hoping it will be the last part of the videos on the solved examples for Basic Physics 2, Electricity and Magnetism. And this part, the problems in this part will be about Kirchoff laws. And we will start with the 37th problem in the documents. Actually, I already prepared the figure before starting the video. So first I'll review how we can apply Kirchoff laws. And remember, we have two laws by Kirchoff's. One is junction law and the other is loop law. So what the junctions were? Actually, the junctions are the points in a circuit at which the currents meet. Some of them come into the junction and some of them may go away from the junction. So before starting, first let's assign a current to each resistor. So let's say this is I1, all right, leaving the 9-volt power supply, and it is passing through a 100 ohm resistor. So we have a junction here, let's call it junction A. So I1 comes here, but then it's going to split into two ways, right? Let's call it I2 and let's call this I3. So I2 and I3 are going away, but while I1 is coming. I1 is coming coming to the junction. So I2 will pass through the 150 ohm, but we have another power supply, so it will give some current. So let's assume that I4 is passing through the 150 ohm resistor, and we came to another junction here. Let's call it B. I3 will come here after passing through 50 ohm resistor, and then let's assume that I5, after I3 and I4 meet at junction B, I5 will go away and pass through the 200 ohm resistor and comes back to the power supply of 19. So we have two junctions at which some currents meet. For junction A, just to remember the junction law, for instance, junction A, I'm going to call JA. We can write this equation. I1 is coming toward the junction A, while I2 and I3 is moving away from junction A, and this should be equal 0. And from junction B again, we can write here I3 and I4 are coming toward the junction B, and I5 is going away from from junction B. But this current I1 is leaving 90 volt power supply, I5 is coming to 90 volt power supply. It is not possible if I1 and I5 are different. So from here we can write I1 should be equal I5. And if we use these two equations, I1, I2 and I3 equal 0, I3 and I4 will be equal, minus I1 now should be equal to 0. We can find, let me see if I'm correct, I2, I3, I4. Okay, so if I write I1 for this one, so I1 minus I3 is equal I2. So I1 minus I3, this I4 also should be equal I2. We can derive from these equations. We are going to use them later. Just we are now playing before moving to the solution of this problem. Now, these are the equations we obtained by applying junction law of Kirchoff's. Now, the loop laws. We also have loop laws. What Kirchoff's loop law says? Through a loop, the total electric potential difference should be 0. So what is a loop? Actually, each eye of this circuit is a loop. So we have two loops in this circuit. One is here. We are going to follow this way. So this is first loop, and the other is here. This is the second loop. So if we follow this path through the loop and write the electric potentials, we need to have we will have 0 at the end. So from first loop, I'm going to call L1 loop first. From loop first. So this is again, remember our notation. The power supplies has two sides. One is longer than the other, and longer side means positively charged, and the shorter side means negatively charged. And here again, positively charged is the longer side, and negatively charged is the shorter side. Actually, this is the direction also of the current current provided by the power supplies. So actually, this is providing a current in this direction, which is the opposite direction we choose, and this is providing the current in this direction, which is in the same directions we are going to move. So from the first loop, see, we are following this direction, so 9 volt. All right, we came to the resistor here, and we are following the same direction with the current, but we need to put a negative sign because resistors eat up energy, so they contribute negatively to the loop. So I1 times 100 ohm, and then we are following here, we have I3, but we are following the same direction, so minus I3 times 50 ohm, and then we come to I5, but it is already I1, we derived it, but we are following the same direction, so it's going to be minus I1 times 200 ohm should be equal 0. I'm going to rewrite these equations, okay? We are just now refreshing our memory about Kirchoff laws. Now we can also apply the same same approach to the second loop. So L2 is the loop, the second. So we are going to follow here, but now we are following the opposite direction of this, the current provided by this power supply. So I need to write minus 6 volt, and now we are following the same direction with I4, but I4 is already equal I2. So minus I2 times 250 ohm. Now we are following, now we came here, but I3 minus, but I3 is in the opposite direction, so minus I3 times 50 ohm. And what else we have? Okay, we forget this one, so we came to here, I2, we were following the same direction with I2, so minus I2 times 150 ohm should be equal 0. Alright, these are the equations actually Kirchoff's law gives us, and we are going to use these equations to solve problem 37. Okay, now this is just a reminder. Let me draw the same circuits again in a clean way. Alright, we have this. This, so we have another power supply, but yeah, in this direction, and there, resistor here. So it is 9 volt, and let me see, it is 9 volt, it is 6 volt, if I'm right. So this is 100 ohm, this is 150 ohm, this is 250 ohm, this is 50 ohm, and this is 200 ohm. And this is junction A, B. Now I'm assigning the currents I1, so it is going to be I2, I3, and what else we have? I4. I4 is actually equal I2, and I1 is again here. Now, actually I just choose the direction of the currents arbitrarily, okay? You are free to choose any direction for the current. At the end, if you choose the wrong direction, you will find negative for I1 and I2. If you solve the equations and find I1 is negative, it means I1 will be in the other direction, but the magnitude will be correct, okay? So you don't need to worry about the directions of the currents. Now, we are going to write the equations what we have. So all right, let me just remind myself. All right, we have these equations now. Okay, just also I need to remind myself to the equations. Okay, right, one, choose this way. All right. Now we have 9 from the first loop, 9 and minus 250, where is, okay, it's not this one. All right, epsilon 2, actually I call it epsilon 2, yep. So I have 9 volt, but I'm not going to write the units because I have limited space here. 9 volt minus 100 I1 passing through here, minus okay, also we have 200 here, so in total we are going to have 300 I1 and minus 50 I2 will be equal 0. And for the second one we are going to have 6, but minus 6. This is from the first loop, and for the second loop now I'm writing, all right, minus 250 I1 and plus 50 I2 and minus 150 I3 will be equal 0. We also, have the junction equations. Okay, let me just write it. So I1 minus I2 minus I3 is equal 0, and from the other junction, but we already use it, I2 plus I4 minus I5 are equal 0, but when we get I5 is equal I1 and I4 is equal I2, we are going to have the same equation. Alright, actually the question is asking find the power dissipated in each resistor. It means, let me remind you, remember the energy dissipated from a resistor is the current squared its resistance times T. But the power, let me remind you the definition, power is delta U, the time. Actually the power is the energy dissipated in a resistor by unit time. So actually the power P will be equal I squared R. And maybe I forgot to mention about its unit, but you can check its unit. The current has a unit ampere and R has a unit ohm. So its unit is ampere squared ohm. We call it watt. Okay, and we show it with W watt. All right, we are going to use it. Okay, so to calculate the power from each resistor, we need to find the currents passing through the resistors. Actually, the question is the same as calculating I1, I2, and I3 by using these equations. Actually, I leave the mathematical steps to you, and if you solve these three equations, you will find, I'll give you the result directly, you will find I1 will be equal 0.025 ampere, I2 will be equal 0.03 ampere, and I3 you will find in this configuration, I3 will be equal minus 0.005 ampere. Now again, we have a minus sign. It means I show I3 is moving in this direction, but see that minus sign says that actually I3 is moving in the other direction. Okay, if I chose this direction in the beginning, I would find positive, but since I choose the wrong direction, the calculation corrects me with a negative sign. Okay, it says choose the other direction for I3. But for power it's not important, so we are going to use the power equation to calculate the power dissipated in each resistor. Alright, so again the power P will be equal I squared over R for each resistance. So power first will be equal, let me just take my notes, it will be like I1 squared or times R1. R1 is the resistor with 100 ohm, so it is like 0.025 ampere squared times 100 ohm. So by using your calculator, you will find 0.0625 watt. All right, sorry about my space, actually it is quite limited. Now the second one, the power 2 will be equal I2 squared R2, and R2 is the resistor of 50 ohm. It's going to be, what was our I2? It's like 0.03 ampere squared times 50 ohm, and you will find the power dissipated in this resistor is like 0.45 watt. And keep going, actually you can calculate P3 because it's going late and I'm losing the light, so I'm going to give you the hint. All right, so you can keep calculating the calculating the power dissipating in each resistor. Okay, so this is a sole example, actually giving you a hint or giving you an idea how we can apply Kirchoff's laws to analyze an electric circuit. Actually, it's not complicated. You need to just be careful. And again, I recommend you to check my calculations in case if I made some mathematical mistakes. Actually, checking for my mistakes, it will be a good practice for you as well. So before concluding this video, I wanna talk about the RC circuits. All right, the RC circuits actually are used to charge or discharge. Let me just write here, RC circuits. We are using RC circuits to charge or discharge a capacitor. And actually, when we discuss charging or discharging a capacitor, I usually connect the capacitor to the battery directly. But in real life, we don't do it usually. Let's say this is our power supply, all right, V, and I'm going to use it to charge a capacitance C. If I do it like this, actually the capacitor will be full quite quickly, very quickly, and we can just pull off the capacitor. So we usually add a resistor to the system when we are charging this capacitor. So by adjusting this resistance of this resistor, we can charge this capacitance slowly or fast. So small resistance, fast charging, large resistance, small charging. Now, actually this is nothing but the question, the problem 38. When we are charging this capacitance, actually we are going to have some electric potential difference between the plates of the capacitance. And problem 38 is asking find VC as a function of time. How we can do it? Actually, we are going to apply Kirchoff's loop law to calculate this one. So let's say this is the positive side and negative side. So if we follow this way to calculate to write the Kirchoff's loop law, again like V and I go like this, all right? So I times R, and here plus or minus here actually minus VC will be equal 0. What is VC? We know actually this is Q over its capacitance, right? And what is I? Actually, it's nothing but the total charge passing through these lines per unit time, and actually this is the derivative of the total charge passing through the lines with respect to time. So if you put all of them into this equation, V is here minus I. For I, I'm going to write dq over dt, and minus Vc, I'm going to write q over c will be equal 0. To calculate what is Vc as a function of time, or what is q as a function of time, we need to solve this differential equation. I'm not going to give you all the mathematical steps, but if we solve this differential equation, we find the total charge accumulated in this capacitance as a function of time is like Q0, the total maximum charge at the end, times 1 minus e to the power of minus t over RC. R is the resistance here, and C is the capacitance, and T is the time. But by using that equation, Q over C, to write it in terms of the Vc, so QT, if I divide it both sides by C, we are going to find Vc as a function of time. This Q0 over C should be equal this, right? The potential of the power supply, 1 minus e to the power of minus t over RC. So this is the electric potential difference between the plates of capacitance at any time as a function of time, all right? When t goes to infinity, we can assume that the capacitance is fully charged now, and its potential, it's going to be 0, its potential will be equal V. All right, this is charging of the capacitance, and this is the electric potential difference between the plates of capacitance as a function of time. And let's keep going, last subject. Now discharging of a capacitance. When we discharge a capacitance, actually we have the capacitance, full capacitance now, so Q0 and Vc is the electric potential difference between them, and we discharge it over a resistor, okay, R. And now again, we are going to use Kirchoff's loop rule. Let's say it is moving, the current is moving this direction. If I write it, now Vc is providing some currents to the circuit, so its energy will be positive, minus the current times R will be equal 0. And just let me write Vc will be equal Q as a function of time over C, the total charge remaining in the capacitor, and I will be equal dq over dt. So if I plug them into this equation, Q over C minus R times dq over dt should equal 0. And if you find the q, if we solve this equation, q as a function of time will be q0 times e to the power of minus t RC. And if we divide both sides with its capacitance, we are going to find Vc as a function of time will be V in the beginning, all right, when it is full, times e to the minus t RC. All right, so this is the change of the electric potential difference between the plates of a capacitance during we are discharging it. When t goes to 0, actually it's going to be 0, and actually it's at t equals 0, the capacitance will be empty fully, so there is no potential difference. So t goes to infinity, the electric potential difference will be 0 at the end. And just before concluding, I'll give you the definition. R times C, you see the factor R times C here. R is the resistance of this resistor and C is the capacitance, and its multiplication. Actually, you can check the unit. Actually, this is a good practice. Check its unit, all right, the R and C, and you will find it's in the unit of time, all right. Its unit will be second, and we call this characteristic time of the capacitance. All right. Sorry about this last part because I lost the daylight. So hope you can read from the board. You can read the last part from the board. I'm going to finish this video here. And if we need, I can provide you more video with solved examples, but I think we covered plenty of solved examples to cover all the subjects we discussed so far. But just once again, I suggest you to solve the problems yourselves. Actually, these videos are just providing you some hints, some approaches, some insights, okay? You can use, but you can use while you are studying yourself, and hope you are enjoying these videos. In next video we are going to move to the new subjects, and I hope we may include I hope we can include the magnetic fields to complete this semester. All right, hope you will find these videos helpful, and hope these solved examples will be useful for you. You can find the problems in the documents I uploaded online already, so you can follow the problems while you are getting some help from these videos while you are trying to solve all the problems. All right, take care of yourself and hope you are enjoying these videos.